In the name of Almighty God, I'm Master Sankoshi, and today I want to talk about problems energy, which is a subsection of chapters for physics GRE. The following three questions refer to the diagram: a pinball machine launch ramp consisting of a spring of force constant K and a 30-degree ramp of well length. And now I want to go through the examples 1.8. Let's revisit the quarter circle ramp problem, example 1.6. But this time suppose that after exiting the ramp, the block slides along a flat surface with a coefficient of friction micro. How far down this surface does the block travel before it stops? Now we could start where we left off by using the speed v is equal to square of the 2gr at the bottom of the ramp, then computing the kinetic energy and continuing from there. But that would actually be too much work, no pun intended. Instead, let's just apply the work energy theorem directly. The block's initial energy is mgr, the fractional force is micro mg along the flat surface. Recall the micro is the proportionality constant between the normal force and the fractional force. And so after traveling a distance x, friction does work micro mgx. When the block has stopped, its energy is zero. Applying the work energy theorem, we have mgr minus micro mgx is equal to zero, which x is equal to which is included to the x is equal to r divided by micro. That's it. We never even had to solve for the velocity at the bottom of the ramp. At a sanity check, we can examine the limiting case micro, which is give to the zero, and micro which is has a tendency to the infinity. As micro is going to the zero, there is no friction, so the block never stops. And when the as a micro is has a tendency to go to the infinity, infinite friction means that the block stops right away. You can do a similar analysis for r to go through has a tendency to go to the zero and infinite. So I want to go through the 1.4 chapter of momentum. If you have gotten this far in physics, then you don't need to refresh on the physics of conservation of momentum. Some of the problems, however, take a bit of practice to learn to solve quickly. In general, you just need to remember that momentum is always conserved in a system in the absence of external forces. This caveat about external forces is sometimes important. For example, if two bars collide in the mid-air, the total horizontal momentum is conserved, but not the total vertical momentum, because gravity is acting in that direction. In fact, the vertical momentum will continually increase in the downward direction according to the Newton's second law, where F is equal to P. The trick with momentum problems is just to be sure that you are counting all types of momentum, linear and angular, and writing down the current conservation equations. The next subsection for this momentum section is 1.4.1 linear collisions. This class of problems involves point particles that undergo collisions or explosions for the purpose of the GRE. If things are colliding, try conservation of momentum first. Collisional forces can be arbitrarily complicated, but because they are all internal among the colliding particles, the total momentum is conserved. As long as there are no additional external forces such as gravity, you just need to set the initial momentum equal to the final momentum and solve for the necessary variables. A special case is when the initial and final energies of the system are the same. This is known as an elastic collisions, and imposing conservation of energy can give you an additional equation to solve to find outgoing velocities. For example, don't assume a collision is elastic unless you're explicitly told so, as this can lead to many traps answered. See example 1.9. Solving momentum conservation problems like this one invariably reduces to solve systems of linear equations. This often gets complicated, and if you're like most people, it's easy to make algebraic errors. Don't do that. Exhaust all limiting cases and dimensional analysis arguments before doing algebra. After this, if you think the algebra is easy, then do it. If you think it will be messy, just keep it and come back later, since you may not even have time to finish the exam. Trig is essential. Chapter 1.4.2, which is a subsection for momentum, and it is a rotational motion and angular momentum. Like linear momentum problems, the game here is always to write the angular momentum in the initial state and in the final state, then set the two equal. The angular momentum, a point particle of linear momentum p, is defined by the equation of 1.16, which is L is equal to R multiplied by P, where E is the vector from a chosen reference point to the particle. Remember that rotational motion is always defined with respect to a reference point or axis. For an extended body, we also have the equation of 1.70 when L is equal to I omega, where I is the momentum of inertia and omega is the angular velocity vector. Conceptually, I plays the same role as the mass m in the definition of linear angular momentum p is equal to mv, extending the metaphor, the analog for of force F for rotational motion is the torque. The torque is equal to R multiplied by F based on the 1.18 equation. Classic problems include merry-go-rounds and spinning discs. For instance, if a person jumps onto a spinning disc with a known moment of inertia, how does the rotational velocity change? Just equate L is equal to I omega in the initial and final step states. We wrote angular momentum and torque in their vector form for completeness above. Note, however, that the vector form is only really needed for the definitions of L and the torque. The analogues of the equation P is equal to, I mean that rho is equal to mv, and f is equal to differentiation p divided by t are only used on the GRE in their scalar forms. The equation 1.19 L is equal to I omega, and equation 1.20 is torque is equal to the differentiation L based on the t or time. Problems involving angular momentum can also be conceptual, asking for the configuration of momentum, velocity, and acceleration vectors for a system involving rotational motion. The key point to remember is that the angular momentum vector L is generally parallel to the angular velocity vector omega, which points along the axis of rotation just like an object's linear momentum is parallel to its velocity. The direction of L is determined by the right hand rule. Curl the fingers of your right hand in the direction of rotation, and your thumb gives the direction of L. More advanced classical mechanics text field discuss rotating reference frames, which are mostly beyond the scope of the GRE. All you need to know is that a reference frame rotating at constant angular velocity is not inertial, but nonetheless, one can write a formula resembling Newton's second law, where F is equal to mr at the price of the introducing friction forces, which only appear because of the non-inertial choice for coordinates. The equation of 1.21 is force centrifugal is equal to minus m omega O to the power of 2r, and F Coriolis, which is equal to minus 2m O multiplied by V. The centrifugal force, which we emphasize once again, is not a real force, it's the apparent force on an object in a uniformly rotating from a frame that pushes it away from the axis of rotation. The Coriolis force vanishes if the object is stationary in the rotating frame, but often appears in the context of the Earth's rotation, which defines a rotating frame, unless the motion of the object is defined with respect a rotation and rotating frame, in which case you typically need to use the Coriolis force. We recommend sticking with the inertial frames to avoid confusion. Now I wanna go to the another subsection of the momentum force, which is 1.4.3 moment of inertia. As we have seen, an object's moment of inertia is analogous to its mass in the context of rotation, but unlike mass, it depends on the distance from the center of rotation. Let's start with a point particle of mass m. The moment of inertia scales with the radius as m is equal to mr to the power of 2 based on the equation 1.23, which accounts for the fact that if at fixed rotational frequency the particle will have a higher linear velocity at higher radius. Thankfully, the moment of inertia of a system of many particles is just the sum of the individual moments of inertia. Strictly speaking, this is only true if the system is rotating about one of its principal axes, but these correspond to various axes of symmetry, and practically all the rotating objects you will see on the GRE are symmetric to some extent and rotating about their axis of symmetry. So to the so to the best of our knowledge, you can ignore these subtly for GRE purpose. The exception is in the problems involving precision, which we haven't yet seen appear on the GRE. The figure 1.10 illustrates a penny is rotated about two axes x1 and x2. The moments of inertia for rotation about each axis are related by the parallel axis theorem. So we can generalize to extend objects with arbitrary mass distributions by integrating I is equal to integral r to the power of 2 dm, where dm is a infinitesimal mass element which can depend on position, and the integration is taken over the entire system. Conceptually, objects with more mass further from the axis of rotation are harder to rotate and have a larger momentum of inertia. Typically, the integral for moment of inertia is solved by changing integration variables to spatial variables using the density dm is equal to rho dab. Note that if you are given the density, for example, rho is equal to r to the power of 3 for a sphere, you actually have to do two integrals. One to set the total mass m equal to integral rho dv to eliminate the constant r, and the other to compute the moment of inertia. The GRE does provide the formulas for the moments of inertia for rods, disks, and spheres on the equations page at the beginning of the test. Typically, that is sufficient. Tau, it is useful practice to compute these formulas. The parallel axis theorem is a fast and frequently invaluable tool for computing the moment of inertia of systems built out of smaller pieces whose moments of inertia are now. If we know the moment of inertia R of a system of mass m rotating about an axis 2, Its center of mass, cm, then its moment of inertia about any axis parallel to the cm axis is given by the I is equal to ICM plus m r to the power of 2 based on the equation 1.25, where r is the distance between the CM axis and the parallel axis. For instance, the moment of inertia of a penny rotating about an axis perpendicular to the center of one of its faces is given on the GR formula page as I is equal to 1 divided by 2 m r to the power of 2, the moment of inertia of the penny when rotating about an axis that passes through the edge of the penny. See the figure of 1.10 would just be I is equal to 1 divided by 2m r to the power of 2 plus m r to the power of 2 is equal to t 3 divided by 2m r to the power of 2. And now I want to go to the another subsection of momentum force, which is a 1.4.4 center of mass. For reference, the center of mass of an extended object of mass m can be calculated similarly to the momentum of inertia using RCM is equal to integral RdM divided by m based on the equation 1.26. Instead of weighting the mass by the square of the distance from the axis of rotation, the center of mass weights the mass by the displacement from the original. In the principal equation 1.26 is actually three integrals, one for each coordinate. The corresponding formula for a system of point masses just replaces the integral by a sum. RCM is equal to sigma I, which the number of I is three-dimensional, RI divided by m. In particular, for a single mass m at a position R, the center of mass is just R, as it should be. See the example of 1.10. So thank you so much for watching my physics tutorial video until the end. And also, if there is any concept simulation, you can download it from the github.com/masterscape. Today is 30th of March 2026 and time is 8:22 p.m.